right, now we're going to be talking about measures of position and outliers. So sometimes we want to know how far away it is without saying the standard deviation is 15, the average is 60, so 77 is how much, right? So what these measures of position are called z-scores right here. These are our measures of position, and they're going to tell us how many standard deviations away something is from your average. Now, we're also going to be talking about percentiles. We're going to define and talk about that. We're going to determine and interpret quartiles. We're going to determine and interpret the interquartile range, which we've talked about. And then we're going to check a data set for outliers. And I'm going to teach you how to do that by hand. And then I'm also going to show you how to do that on the calculator. We have two formulas for z-scores. This will be on your formula sheet, but this is something that you do need to remember. Z-scores are going to play an important part in hypothesis testing, which is something that we're going to do later. Because remember, this is the number of standard deviations away. This is going to tell us if it's a usual distance, an unusual distance, and what we can kind of expect. So when we compare z-scores, we have to first of all figure out how to find a z-score, and then once we find the z-scores, we're going to compare and interpret. So we find, we compare, and interpret. So find, compare, interpret. All right, so the mean upper arm length of 19-year-old males is 38.6. Now, this is where I use different colors. I kind of try and group things together. I've got to keep everything organized because I don't want to get the data mixed up. Because to calculate a z-score, I need a value minus the mean divided by the standard deviation. So I need those two things, and I usually read it that way. So it's your value minus your average divided by your standard deviation. So it says the mean upper arm length of 19-year-old males is 38.6 centimeters with a standard deviation of 2.9 centimeters. The mean upper arm length of 19-year-old females is 35.8 centimeters with a standard deviation of 2.8 centimeters. Who has a relatively longer upper arm length? A male whose upper arm length is 41.1 centimeters, or a female whose upper arm length is 38.4 centimeters. I can't tell that just from looking at that data because it's relative to that specific average. So if you remember in the last 3.2 that we talked about, how far away is it really? Is it really far? Is it not really far? So that's why we interpret it in terms of the standard deviation, because that helps us determine truly how far it is from that specified average value. So the first thing I'm going to do is I'm going to calculate the z-score for the male. So the z-score is the value, which our male has an upper arm length of 41.1 centimeters, minus the average, which is 38.6 centimeters, divided by the standard deviation of 2.9 centimeters. Z-scores are typically rounded to 2 decimal places. So when you calculate this, make sure you round appropriately. All right, this is 86 hundredths of a standard deviation above the mean. We would expect this to be positive because this is above the mean. It's not below, it's above. So we do expect that to be positive. So this individual has an arm length that is 86 hundredths of a standard deviation above the mean. Now we're going to calculate the female value. So this female has an upper arm length of 38.4 centimeters with an average of 35.8 centimeters and a standard deviation of 2.8 centimeters. When we calculate this tells us that this female has an upper arm length that is 93 hundredths above average. Now, when we're looking at whose arm is relatively longer, we're looking at the position of the standard deviation. So we really have to look at what is better in this case. So if relatively longer means it's going to be further from the standard deviation. So here's one. So we have our male who is, say about here. We have our female who is about here. So clearly in this situation, the female's upper arm length is relatively longer compared with her peers. And that is why we would say the female upper arm length is relatively longer because the z-score indicates her length is higher than the male. So when you're comparing z-scores, it's important to understand what better is. So if I'm running a race, I want to be lower because the lower or the further from average I am on the left-hand side, the quicker I am. So really pay attention to what it's asking you. All right, to interpret percentiles, the kth percentile, K could be anything. It could be 72, it could be 15, it could be 41, things like that. It is denoted piece of K, is a value such that K percent, this is where you need to pay attention, K percent of the observations are less than or equal to that value. So when we're looking at percentiles, we're looking at the left side of that value. So when I tell you to interpret a percentile, the Graduate Record Examination, GRE, is a test for admission in many U.S. graduate schools. The University of Pittsburgh Graduate School of Public Health requires a GRE score no less than the 70th percentile for admission into their Human Genetics MPH or MS program. Cited as a source, interpret the admissions requirement. All right, so when we go to interpret this admissions requirement, it's important to note that requires a GRE score no less than the 70th percentile for admission. Now, if I'm in the 70th percentile, what that means is that whatever my score is, so say my score is a 1200 or something, that means that 70% of all individuals who took the test scored at or above my threshold, at or below. Okay, that doesn't mean that 70% had to score less. Technically, 70% of individuals could have scored at my score. That's where it fell. Now, is that likely to happen? Definitely not. But could it happen? Yes. So what does it mean when I say that the University of Pittsburgh Graduate School of Public Health requires a GRE score no less than the 70th percentile for admission? What that means is that here is how the scores are laid out. Here is the score at the 70th percentile. So we have 70% at this score or below, and then everybody else, the top 30%, are scoring over here. What that tells me is that I have to be at this score or above in order to qualify for admission into the Pittsburgh Graduate School of Public Health. All right, so determine and interpret quartiles. Remember, we've talked about quartiles, and you can see here, when you're looking at quartiles, you start with your minimum value, go to your maximum value. We first divide it into 50%. So this is at the 50th percentile. So this is the lower half, and then we have the upper 50%. So if you think about quartiles, you think quarters, and that's exactly what happens. We have our data divided into 25th percentiles. So once we find the median, then we're going to find our lower quartile, which is the median of the lower half. And this is going to be my 25th percentile. So all data points are at or below, 25% of all data points are at or below that value. And then we have our median, which is the middle, and then our 75th percentile, or our upper quartile, is the median of the upper half, which is what we've talked about. So that is our 75th percentile. And then, of course, we have 100% of the data will fall at or below the maximum value. Okay, 0% of the data is going to be below the minimum value. And that's kind of what we're looking at there. So it says finding quartiles, and we've done this. Arrange the data in ascending order. Determine the median or second quartile. Divide the data set in halves. The observation below to the left of the median and observations above the median. The first quartile is the median of the bottom half of the data. The third quartile is the median of the top half of the data. We did this with some data previously. We have 5, we have 18, 23, then we have 26, I have two 23s, then we have 26, 36, 43. Okay, so if we're finding quartiles, remember you find the median first. So my median is right here. So M, which is also Q2, which is also the 50th percentile, is 23. So we have 23. Now I could also write that as P50 is 23. So those are all the ways that you can write that. Now we find the median. So for Q1, which is this value right here, remember Q1 is the same thing as P25 because it's the 25th percentile. And that tells me that the 25th percentile is at 18. Or is 18, I should say. And then the 75th percentile, or the upper quartile, Q3, which is the same thing as P75, is going to be 36. Now, we typically use Q1 and Q3 for this, but it doesn't mean that you can't use the other notations. And remember, 25% of all values are at or below 18. 75% of all values will fall at or below 36. And then 50% of all values will fall at or below 23, which we can see is true. Okay. You know how to find quartiles using your calculator. And remember, quartiles using your calculator are under one variable stats. And then you scroll down to your 5-number summary, which is what we're going to talk about in the next lesson, and find Q1 and Q3. Okay, now let's talk about the interquartile range. So the interquartile range is the range of the middle 50% of the data. That is something that I will put on your test. You need to be able to define and understand what the interquartile range is, not just plug numbers in and find it in the calculator. So what am I actually asking you? What am I actually asking you to find? Okay, so it says find and interpret the interquartile range of the data from either finding quartiles example above. So we did this data right here, and I put 76, and it's clearly 36. And when we want to find the interquartile range, we subtract those two values. So then Q3 minus Q1 is 18, because it's 18 minus 36. All right, so let's talk about which measures to report and when to report them. So if I'm reporting on data that is either skew or symmetric, so we've already talked about this, but this is a good time to reiterate that fact. When the data is symmetric, our measure of center is the mean, and our measure of dispersion or spread is the standard deviation. If my data is skewed, we have to use resistant statistics. Okay, so when it's skewed, you have to use your resistant statistics. So this is a good way to also remember which ones are resistant. So we're going to use things that are based on position, not based on average. Okay, so based on position, not based on average. So we're going to use the median, and we're going to use the interquartile range. All right, so now let's talk about how to check a data set for outliers. This is our final objective for this lesson. So extreme observations are referred to as outliers. Outliers can occur by chance because of error in the measurement of a variable during data entry or from errors in sampling. So for instance, 76 in this case would have been a major outlier, and it would have been a data entry error. And I mean, technically it could have also fallen under a measurement error if I'd actually measured that data, but in this specific case, this 76 would have been a data entry error. So those things happen and cause outliers in our data. Now, when we check for outliers, you determine the fences. Here are your formulas. You will have those formulas. And then if a data value is less than the lower fence or greater than the upper fence, it's considered an outlier. So here is how you are going to find outliers by hand, and then I'll show you how to do it on the calculator. So by hand, the first thing you're going to do is you are going to find your lower fence and you're finding your upper fence. So we're going to do a number line here. And we're going to plot our fences on this number line. So for my lower fence, it is your lower quartile, Q1, minus 1.5 times the interquartile range. So I take my lower quartile, which was 18, minus 1.5 times 18. This shows me that my lower fence, and I'm double checking my numbers here, is going to be 18 minus 27, which is -9. So -9 is the cutoff for things to be an outlier. Next, we find our upper quartile, or our upper fence, excuse me. That is your upper quartile plus, this time, 1.5 times the interquartile range. All right, once we calculate this, our upper quartile was 36 plus 1.5 times the interquartile range, which is 18. That gives me 36 plus 27, which is 50 plus 13 and 63. So my upper fence is at 63. Now, anything that falls outside of those, I have to mark as an outlier. I usually plot my max and my min first. So my max is 5. So the max is, say, here. The min is, I said that backwards. The minimum is 5. The maximum is 43. Both of these values fall inside the fences. So they are not outliers. So for this particular data set, there are no outliers. All right, so we're going to do one more example. We're going to look, and it's going to be very obvious what our outlier is, but we're still going to prove why it is an outlier. So here is going to be our data set. Now we're going to find our quartiles. We're going to find our interquartile range, and then we're going to figure out which ones or one or ones are outliers. Our lowest value is 10. Our next is 15, 22. Then we have 30, 45, 60, and 330. 330 would skew our average significantly, and it is definitely going to be an outlier, but let's prove why it is. Our median or 50th percentile is 30. Our lower quartile, or Q1, is 15. Our upper quartile, or Q3, which is also the 75th percentile, is 60. Now, to find our fences, because we have to know what our fences are before we can figure out what our outliers are, we need the interquartile range. So the middle 50% of data range between 60 and 15, which gives us an interquartile range of 45. Once we know what our interquartile range is, we find our lower fence. So we're going to take our lower quartile and subtract 1.5 times the interquartile range. When we calculate this, we see that we get a lower fence or a lower bound for our data of negative 52.5. So our lower fence right here is negative 52.5. Now our upper fence is going to be the upper quartile plus the 1.5 times the interquartile range, and that gives me 127.5. Now, any data point that falls outside of this range is going to be an outlier. So when I plot 10, 10 is definitely here somewhere. Then we have 15, which is pretty close to here. 22 is in here. 330 is going to be way over here somewhere. It is for sure an outlier because it falls outside of that fence. 30 is inside the fence, 45 is, and 60 is. So 30 in this case is our only outlier. And let's look at what that looks like on the calculator. So when we're looking at finding that outlier, we're going to go to Stat. We're going to edit our list. We're going to enter those data points. So I'm going to clear that out, hit enter, and I type in those numbers. So again, the numbers were 10, 15, 22, 330. Then we have 30, 45, and 60. Once we have our data entered, we're going to plot it in a box and whisker plot. So we're going to go to second y equals. We're going to turn the plot on. This time we want a box and whisker plot with outliers. So we're looking at this plot right here. That plot is on in my calculator. Our data is in list 1. And then we zoom 9. And that's going to graph that data for us. Okay, so zoom and then option 9. And we can see there's an outlier over here. So this is what our box plot looks like. We'll eventually describe that and describe its skewness, okay? And in order to determine what this is, now obviously we know the data, but if we didn't know the data, we would say, okay, what is this number? So we're going to hit the trace button. And then we're just going to right arrow over until we see that this max is an outlier because it's outside of that box plot right there. Okay. And that is how we determine that. Now, this is what it's going to look like if the data does not have outliers. So I'm going to go ahead and go to Stat. I'm going to edit. I'm going to plot this in list 2. So we have 23, 36, 23, 18, 5. Then we have 26 and 43. Now, notice I was just typing over data points. That's okay. The only problem is we have to make sure we delete any extra points before we go to plot this. Now we're going to go to second y equals. Stat plot is on, but this time we want it to plot list 2. Once we tell it to plot list 2, we're going to hit zoom. And of course that goes back to alpha because I was on that. So zoom option 9. And we can see that there are no outliers because there are no little points plotted outside of this box plot. And that's how you're going to tell the difference between when there are outliers and when there are not. And if you have any questions, make sure you email me. And that is what your assignment's going to be over. And we will do our notes for 3.5 whenever we return.